So if you recall the part about affine varieties, the next thing there after the Nullstellensatz was discussing the coordinate ring of the affine variety, subvarieties, and the Zariski topology. And here we're going to do exactly the same. And with a few twists, everything works similarly. So first, the coordinate ring. If y in Pn is a projective variety, we define its homogeneous coordinate ring to be the quotient of the full polynomial ring in n+1 variables modulo its projective vanishing ideal. We have seen that this is a homogeneous ideal inside this graded ring. And so by the little lemma that we had about graded rings, this is again a graded ring. And to see a few examples, when you have, for example, the full P1 inside P1, its ideal is just a zero ideal, so you don't quotient out anything, and you could just get back the full coordinate ring. And a bit more interestingly, if y is the vanishing locus of such a linear polynomial, we have seen then it's a linear subspace inside P2, then its coordinate ring is the quotient of this ring by this single ideal. And then you can, well, first of all, you should check that this is indeed the ideal here. This follows from the Nullstellensatz because it is a prime ideal, so it's its own radical. And then, well, if you look at this, you see we can use this ideal to eliminate one of the variables, for example, x2. And so it's isomorphic to the ring K of x0, x1, which was the same thing as this P1. And later we can actually see that this y is isomorphic to P1 as an algebraic variety. But for now, let's make a few more comments. So the first is, even though this is called a homogeneous coordinate ring, it's still, the elements of S of y still don't make sense as functions in contrast to the affine case. Because, for example, f equals x0 in SP1, you see if you evaluate it at two different representatives of the same point, you get two different numbers. So it still doesn't make sense to evaluate these things at points. But what is true is that if you have a homogeneous element in the coordinate ring, then its vanishing locus is well defined. And here one has to be slightly careful because being homogeneous inside this quotient means you have a homogeneous representative inside here. And then asking for this equation for that representative makes sense. But you should really be careful because a homogeneous element can also have non-homogeneous representatives for which this condition wouldn't make sense. You have to really make sure you use the correct notion of degree and so on this quotient ring. Okay. And then, well, the next thing on our task, once we have the coordinate ring, we get relative versions of the vanishing loci and vanishing ideals. So if y is a projective variety, then for any homogeneous ideal inside its coordinate ring, you get this vanishing locus, just the points where the homogeneous representative of f vanishes. And sometimes if you really want to emphasize both the relative to y and projective, then we might use this notation here. And similarly, if x in y is any subset, then its vanishing ideal is defined as the ideal generated by all homogeneous elements of the coordinate ring vanishing at all the points of x. And so this is clearly a homogeneous ideal inside S of y. And all the subsets x inside y of this form vanishing locus of j, as above, these are called the projective subvarieties of y. And as a little remark, just as for affine varieties, this is the same thing as a projective variety in this ambient space Pn, in which the y sits, which happens to be contained in y. Similarly, as we have seen that the affine subvarieties are just the affine varieties contained in the corresponding variety. Okay, so we have these relative conditions, and let's see one example. So we start with Y being the vanishing locus of such a linear system. We could draw it like this inside P2. And then we can take the relative vanishing locus of one more equation. And that equation, we have already chosen a representative which is homogeneous of degree 2. This thing here vanishes on such a circle like this. And then this relative vanishing locus is the vanishing locus in the entire P2 where the first equation vanishes and then this extra equation. And then we can use the first equation to eliminate the variable x0, right? It's minus x1 minus x2. So we plug this in, and then we can expand this here by the binomial formula, and we get minus 2x1, x2. And this is 0 if and only if x1 is 0 or x2 is 0. Since we're working over the complex number, we don't have characteristic 2. And so we have simplified the solution set. We have this linear equation and this linear equations. And then you can see the two unique points where these intersect are 1, 0, minus 1, and 1, minus 1, 0. These give these 2 points. So these 2 points form a subvariety of Y. And of course, they also form a subvariety of P2, which happens to be contained in Y. So these things are equivalent. So that's an example of subvarieties, and then some remarks. The first is now, of course, we can generalize both the properties of the vanishing loci, which we saw before, and we also have a relative version of the Nullstellensatz, working now with this ambient ring S of Y. And one thing which is useful to know, sometimes this is very practical, is that if you have a projective subvariety X inside Y, then it cannot just be written as a zero locus of finitely many homogeneous polynomials. It follows basically from the Hilbert's basis theorem that you can restrict to a finite set, but you can even restrict these polynomials to have the same degree. And so to see this, imagine you have a bunch of polynomials of different degrees, then the claim is we can modify each of the equations to then all go to the same, possibly higher degree. And for this, you just see the vanishing locus of a homogeneous polynomial f is the same thing as a vanishing locus of more equations where you multiply f by some powers of the coordinate functions x0 up to xn. Because now by the properties of this vanishing locus, the vanishing locus claim that this is the same thing as this vanishing locus union the other one. We have seen the union of vanishing loci is the vanishing locus of the product of things. So this fits. So this explains this equality here. But then you see the vanishing locus of these powers here. This is just the empty set. Basically the same proof as that the vanishing locus of the irrelevant ideal is the empty set. So this little trick allows you to replace the condition f of some degree by a condition of some higher degree. And then when you have, for example, equations of degree 2, 3, and 5, then you can boost the degree of this degree 2 and degree 3 condition, all of them to 5. And then you have one common degree like this. So this might be useful in particular for some exercises. Often it's useful to assume this. Okay, so we can boost these degrees, and then as I said, these properties of the vanishing ideals generalize to the relative situation. And then this shows that both finite unions and arbitrary intersections of subvarieties of Y are, again, subvarieties of Y. And that's very good, because if you remember, where did we use this finite union and arbitrary intersection? Well, this just means that the subvarieties of Y form the closed sets of a topology, and this will indeed be the Zariski topology. So we define the Zariski topology on this projective variety Y by saying a subset X of Y is closed if and only if X is a subvariety of Y. And then there's the usual compatibility check. So for example, the Zariski topology on the variety Y inside Pn is just the same thing as the relative topology of the Zariski topology on Pn. And this uses the fact that the subvariety of Y is just a variety inside Pn contained in Y. So here in this video, we have kind of generalized the coordinate rings, relative vanishing loci, and then the Zariski topology to the setting of projective varieties. And so on our quest to make projective varieties into actual varieties, we have now both defined them as sets and as topological spaces.